Today we're moving on to 7.1. We have worked a little bit with triangles. We've worked a little bit with angles. We're now moving on to quadrilaterals. What is a quadrilateral? Four-sided polygon. So in a triangle, if I were to add up all of the angles, they would be 180. The sum of the interior angles of a triangle is 180. Now, interestingly enough, that's only true on flat surfaces. So if you were on a sphere and you drew a triangle and you added up the angles, they would always be more than 180 every single time. And there are some other surfaces like a donut. If we lived on a donut, which would kind of be nice, right? Live in a sprinkle house. If you drew a triangle on a donut and added up the angles, they would also be greater than 180. But there's another surface called the hyperbolic plane, which is really confusing, and we'll get into that a little bit later. The best way to describe it is it's kind of like the seat of a horse saddle. Okay, so it kind of flexes in a couple different directions. And if you draw a triangle on a saddle, yeah, kind of like a Pringle chip. That's a good way to describe it. And if you draw a triangle on a Pringle chip and add up the angles, they will always be less than 180, which is kind of weird. But we only do geometry on flat surfaces for some reason, even though we don't live on a flat surface. Why don't we? Why don't we teach spherical geometry when we live on a sphere? We only teach flat geometry. It is complicated, that's true. And for most applications, flat geometry is so close to accurate that we just run with it. Right? If we when they set the concrete for this floor in this classroom, right? Is this surface totally flat? Technically, no. The gravity on the earth is going to make it curve just slightly, right? But is it noticeable? No. Why? It's tiny compared to the size of the earth. So for most construction projects, we just pretend that the earth is flat. Okay? When yeah, we're flat earthers. When do we not pretend that the earth is flat? Big projects like highways, yep. If we're flying across the country, yep. If we're driving across the country, we pretend it's flat. But the people who built the roads, they knew that it was curved. Yeah. But the road to Wendover is actually kind of bowed, right? Right, that 60-mile stretch outside of Wendover that is totally straight. Um, yeah, it's it seems like it. Um, another interesting thing is farmers actually deal with spherical Earth all the time because farmer fields are broken into squares for the most part, right? I guess if you're in a wash or by a hill or something, then your field might not be rectangular, but the land ownership is divided up into squares. Well, that's a problem because on a spherical object, if I draw a square here and a square here and a square here, and then I try to put a second row, what's going to happen? Well, the further north I get, the more narrow my squares are, right? So this guy might get 40 acres, but this guy is going to get a lot less than 40 acres. So what do? Well, we make everybody's land a square, but the squares don't line up like you think they would. So when we draw our first square, our first row of squares on the equator, and then the next one, there's going to be a little bit of an overhang, and then a little bit of an overhang. And not every time, but if you look at land, what are they called? Section maps. The squares are all the same size, but they don't line up like you want them to. In fact, when we draw borders, we run into some weird things. Let me see if I can find the one that I'm thinking of. There are two that I know of. Okay, let's pull up Google Earth. You know what? Google Maps might be better. That might be easier to see. Okay. So, Utah. We know that this line is straight, and we know that this line is straight, and this one, but anything that's horizontal is actually curved. And remember, we measured Colorado and Wyoming, and the top border of Wyoming is actually shorter than the bottom border of Wyoming. So let's zoom in on Utah. What do you notice? Do you see that? So this border of Utah is not actually straight. Why is that? Well, we divide it up into rectangles. And the further north you get, the smaller the rectangles have to be, but we don't want them to be smaller. We want them to all be the same size. So it's going to mess up the border sometimes. So when you zoom out, it looks like a perfectly straight line. But when you zoom in, there's a little bit of a jog. So there must be a square right here. And then this square is a little oddly shaped. And then the square above it would be normally shaped. And we have to do that all over the place. So another one, let's see if I can I get a county map? I wonder. Okay, Emery County, right? You see that? So where are we? So south of Emery, south of I-70, down by Mustn't Touch It. So there's one there, and look, there's another one right there. Why do they do that? Well, we want that block to be in the same county, right? We don't want to give part of one block to one in one county and part of another block in the other county. So instead of, if this was a farmer's field, instead of this farmer paying taxes to this county and to this county, they're just going to change the county lines to match up with the farmer fields. And I mean, there are no farms down there, but you guys understand. Yeah. And notice we didn't do it here. We don't need to do it with the we don't need to do it as much with the horizontal lines. Of course, that will still happen. Another interesting thing, have you guys ever been right here? Four Corners? Yes. Is it actually at the intersection of those? It is. But you're right, Easton. It is a little bit weird, so let's zoom in. What do you notice? So back when they built this, and it's really cool, you guys should go there someday. So this point, and when you look on Google Earth, the satellite photo is not going to be perfect with the border lines. So I mean, even though it looks like it's a little bit off, don't freak out about it. I mean, that's only like 20 feet. But look at that. Yeah, what happened? Well, I don't know, 100 years ago, they were using survey equipment that was not GPS based, and they went out in the desert and they figured out this is the four corners of those four states. And they were actually pretty close, but it wasn't perfect. And so later, when technology got better, they realized, wait a minute, those four states do not actually meet where they put that dial on the ground. So instead of lifting up all those buildings and moving them, Congress decided to pass a law that changed the borders of those four states. Yeah, so by the look of this, Utah gained some territory when that happened. So instead of moving the monument, they moved the states and said that is Four Corners. And now here's how, and it looks off. I mean, it may be, but my guess is there's just a little incongruity between the picture and, but yeah, the center of that monument right there is Four Corners. Congress said that is Four Corners, and then they just adapted the four states to match it. And Utah gained a little, and Colorado lost a little. And that's some prime real estate right there. Look what we got. Aren't you glad we got all that right there? Okay, so let's go back to our triangle. We have a triangle where the four angles add up to 180. So what if I drew a quadrilateral? So any four-sided shape, what does it have to have in order to be a polygon? The lines have to connect, and they all have to be straight, right? So here is a four-sided shape called a quadrilateral. If we added up all of those angles, what are we going to get? 360. Why? Well, let's cut it into triangles. You guys see that? So angle 1 plus angle 2 plus angle 3 is 180. And angle 4 plus angle 5 plus angle 6 is 180. And 180 plus 180 is 360. Is that true for every quadrilateral? It is. Every quadrilateral can be divided into two triangles. And each triangle has an angle sum of 180. And as long as we're on a flat piece of paper, the angle sum is 360. What if I had a five-sided shape? We divide that into triangles. So we have 180 here, we have 180 here, and we have 180 here. What if the polygon kind of collapses into itself? It's convex, or sorry, concave. So what if I had, is that still going to be 180 plus 180 plus 180? Well, let's look. Can I divide it into three triangles? Yep, 180, 180, 180. So you will probably see a question like this on the ACT when you take it in, what, a couple months? I don't know when it is. It's in March, right? Oh my gosh. Sorry, you're sophomores. When you take the ACT in a year and a couple months, there will probably be a question on the ACT like this. All right. So now let's get to some calculations. How would we find x? Yep. So we'd add the 55, the 113, and the 111 and subtract those from 360. Okay. Let's see if it gets any more complicated. Same thing here. You could subtract them individually. 360 minus 132 minus 69 minus 67. Okay, easy enough. All right. A 17 gone. So if I were to draw a 17 gone, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17. How many degrees are, if I added up all of those angles, what am I going to get? Well, the question is, how many triangles can you draw? In a four-sided figure, how many triangles can you draw? 2. In a 5-sided figure, how many triangles can you draw? 3. In a 6-sided figure, it's going to be 4. So in a 17-gon, how many triangles can you draw? Not 18, 15. The number of triangles is always 2 less than the number of sides. So for a 17-gon, I do 17 minus 2 is 15. And if there are 15 triangles, how do I figure out the angle sum? Times it by 180, and I get 2,700. So if you add up all of these angles, you're going to get 2,700 degrees. So the process is pretty simple. The number of triangles is 2 less, 2 fewer, than the number of sides. And then just multiply that number by 180. Okay. So how are we going to figure out x? Well, we count the sides. How many sides are there? 1, 2, 3. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Oh, it says 8. That's handy. Okay. So how many triangles does an octagon have? 6 times 180. Yeah, that has 8. Yeah, it says right here, 8. Right, so you take 8. An octagon has 6 triangles, so 6 times 180 is 1080. And how do we find x? Subtract all of those from here. Once you know the angle sum, just subtract off all of the known angles to find x. Hey, it's Friday. Give him a break. All right. I am looking at an unknown shape, unknown to you, and I tell you the angle sum of this shape is 540. How many sides does it have? So we take 540, we divide it by 180, and that gives me 3. What does 3 tell us? There are 3 triangles. So if a shape has 3 triangles, it must have 5 sides. Okay. Now, notice it says convex polygon. So when you get into larger shapes, you can actually create some problems. Let's see if I can do it. So because we have these caves, it's concave, I can't actually split those angles up. So with a larger polygon, you can run into problems with concavity and angle sum. All right. Okay. We're introducing a new word, regular. What does it mean for a polygon to be regular? Well, it's not concave for sure. Okay. Stop signs are regular. The Pentagon building in Arlington is regular. Squares are regular, kind of. Not straight sides. A regular polygon has equal sides and equal angles. So do all octagons look like stop signs? No. But all stop signs have equal angles and equal sides. So squares are regular. The Pentagon building is regular because all of the sides are equal and all of the angles are equal. So if I had a regular hexagon. Okay, now I'm not very good at drawing, but all of these are equal, and all of those are equal. Can you tell me how big this angle is? How would you do it? So 4 triangles, 4 times 180. Yep, 4 times 180. We get 720. What does that tell me? That is the total angle sum for all angles. And there are 6 angles, so I divide this by 6 and I get 120 degrees. Now, as polygons get more and more sides, regular polygons, do the angles get bigger or smaller? Bigger. A triangle has 3 60-degree angles. A square has 3 90-degree angles, or 4 90-degree angles. A hexagon has 3 120-degree angles. And the bigger the polygon, the bigger the angles. Okay? So how would we do a 20gon? And why do we call it a 20gon? Once we get to 10, we kind of quit giving them names, right? 7 is heptagon, 8 is octagon, 9 is nonagon, 10 is decagon, and after that we just kind of say 11gon, 12gon, 13gon. Okay, so a 20gon. What do we need to do to find the angle measure of an interior angle of a regular 20gon? How many triangles will a 20gon have? 18. So 18 times 180 is 3,240. I divide that by 20 angles, and I get 162 degrees. Does that make sense? Oh, okay. So good. Thank you. Okay. There's my 20gon, right? I have just figured out that the interior angle, is 162 degrees. So if I kept this going, how big would that angle be? That would be 18. Okay. So an interior angle is, well, you know what that is. An exterior angle is the angle created when one of the sides extends out, and it's that little angle that is a linear pair to the interior angle. Now, here's an interesting thing too. How many exterior angles does this shape have? It's going to have 20, right? If I went all the way around, if I were to count those up, I would end up with 20, right? And they're all the same size. So if you add up all exterior angles, it doesn't matter the shape. If it's convex, then they always add to 360. Mm-hmm. The exterior angles always add to 360, no matter what the shape is. So keep going. Keep going. Exactly. So if I wanted to know the exterior angle, I can find the interior angle and then find its linear pair. Or I can take 360 and divide it by 20, and I get 18. Okay? All right. We have a shape. I don't know. So here's an angle. I don't know how many sides it has. But this right here is 140 degrees. How many sides does that shape have? How are we going to figure that out? Well, how many 140s are there? I don't know. And if I don't know that, then I can't use that method to figure out how many sides there are. I use the exterior angle, right? So if this is 140, then how big is that? 40. How many 40s does it take to get to 360? So we take 360 and we divide it by 40, and I get 9. So that shape has 9 sides. Okay. That's it. Well, hold on. I think so. Let me make sure that was the last one. Yep. All right. Get to work.